Hello everyone, this is DSS Zindabad and today we are going to discuss the daily challenge of Leetcode, which is longest common subsequence. So let's jump into the problem statement. Given two strings text1 and text2, return the length of the longest common subsequence. If there is no common subsequence, return a 0. Now what is a subsequence? A subsequence of a string is a new string generated from the original string with some characters deleted without changing the order of the remaining characters. So for example, you had something like A, B, C, D, E as the given string. So we can say ACE is the substring of the given string, right? This was the given string. So what I have to do is I have to find the common subsequence length between the two strings that are given to me. So in this problem statement, I understand as an input, I have two strings, right? And as an output, I need to give the length of the common subsequence. That means if I try figuring out all the possible subsequences, I need to give the length of the longest common subsequence. I hope the problem statement is clear. Now let's jump into an approach. Okay, so let's talk about the brute force. Whenever I say brute force, it means the first approach that comes into my mind. So according to the brute force, what I understand is that, for example, the text one that was given to me was A, B, C, D, E, and the text two that was given to me was A, C, E, right? So this is something which is an input given to me, right? So what I have to do is I need to find the length of the longest common subsequence. So what I'll do is I'll say, okay, let's first try figuring out all the possible subsequences of each string and then find the longest common subsequence, right? But this will take a very, very huge time complexity. That for this string, I'm trying to figure out all the possible subsequences. Then I'm storing those subsequences in a particular data structure. Then I'm creating for this string. Then I'm storing it for another data structure. And then I'm comparing these two data structures, right? So it has a very, very high time complexity, almost an exponential time complexity, even more than exponential, right? So what I can understand is that when I talk about this approach, I need to optimize it, right? So for optimization purpose, I say that what I can do is I have to first of all figure out all the possible, right? So we know this, that this is a hint for us to know that for such problems, we can apply something like recursion. So what does recursion say? It says that you handle the base case, rest is something that I'll automatically handle. So herein what I can do is I'll simply use recursion, right? And I'll try solving this problem. Now my recursion will be built upon the base of not creating the subsequences, but comparing the two strings. Okay. So now when I say this, that rather than creating the subsequences explicitly, I'll be just comparing the two strings and I'll be maintaining the maximum length corresponding. Okay. So this is the optimized version in which I'll be using recursion, right? So when I talk about this optimization approach, right, I talk about comparing the strings. Now, why am I saying this? See, I was given that text one string had A, B, C, D, E, right? And text two string had something like A, C, E, right? So whenever I talk about the longest common subsequence, it means it needs to be the same or the common subsequence for both these strings that has been given to me and should have the longest length, right? So what I can see is, I say that if I start traversing from the last index for both of the strings that are present, right? That means string text1 and string text2. So here I see that, yeah, E is similar for both. So whatever is my length value, I'll increment it. Suppose it was 0, so I'll increment it, that yes, 1. Now what I'll do is I'll decrement these because I was standing on the last index. So in the text 1, I am standing on index 3 and I have D corresponding to it. And for text 2 string, I'll get a C. Now I see that D is not equal to C. So in this case, I have two cases. That means I can say that what you do is you keep standing on D and you move the pointer which was there in the second string ahead. Why? That suppose it was something like D here, right? So I'll say that whatever is this remaining part, it might contain this, right? Or what you can say is that you keep, for the text 2, you keep it where it is. That means you keep it on the C, right? But you move it for the other index so that here it was D. When you come here, now you see that, yeah, it is having a C. So here again, there is a match. So whenever there is a match of characters, you can increment the length. I hope this approach is clear to you. Now let's quickly code this up, then we'll have a dry run and we'll discuss its time and space complexity and how further we can optimize it. Okay, so this is the problem statement that we have. What I'll do is I'll say, let's quickly make a solve function, right? So I'll simply say return solve, and therein I'll be passing it the indexes as well as I'll be passing it the strings that I already have. So what I'll do is I'll say that, okay, let's pass the strings that I have, that is text1 and text2, and let's compute the value of its last indexes. So text int n is equals to text1 dot length minus 1. So that gives me the last index, right? Or we can say just the length, we can have it here. And similarly, I can have a variable m for text2, which is basically taking care of the string 2 that has been given to me so that we can access its last index that we have, right? Here I'll pass n minus 1 and m minus 1, right? So now let's create the solve function. It is of int type, right? I'll quickly copy paste this and let's have something as int I and int j, right? So what happens is we'll say whenever we're talking about recursion, we have a base case, right? Then we perform all the possible things that we can do on the given question, right? Here, as we have talked about, we have to find the longest, so it will require us taking a maximum, and then we have the recursive function. So herein, what I'll do is, first, let's write the recursive function, then we'll think of what can be the possible base case for it. So here, as I have just discussed with you previously, that we were basically incrementing the length, right? Whatever we were considering. For example, there I was considering a length variable only when the characters match. So I will say that if text1 I is equal to text2 j, right? In that case, what you need to do is you can have something like int match, right? Okay, let's initialize it outside so that we can access it even after this if block, right? And let's give it some very minimum value. Why? Because if you take the longest, right? So I'll say if it is matching, you update the value of match, that is 1 plus, you call the solve function again, you pass the strings that have And what you do is now for I and j both, because they have matched, right? So that means both of those are coming in my common subsequence. You move both of them. So you'll decrement both of them. Then the other case is when they will not match. So if this condition is not being true, you will have the not match condition. So you can have something like int not match. So here what you can do is, as we saw, we have the possible two opportunities that we can undertake. The first one being that you just move the I pointer, let j as it is, or vice versa. So I'll say what you do is you take the maximum, and now you have to take the maximum for what? You are not adding anything. There won't be any plus one. Why? Because we have not found the similar character. And for the common subsequence to be formed out of two given strings, we need to have the common, right? So I'll simply say take the max, call the first call the solve function, right? And in the first, what I'll do is I'll say I'll be decrementing my I. That means I'm moving on my text one, but my j remains as it is. Similarly, have another solve function, right? Now herein I'll have text one, text two. Now I'll let my I index be as it is, and I'll decrement my j. So that means I'm going to the next index or the next value that I have on my string 2 for comparison, right? And then eventually what I'll do is I'll say return, because what we have to do is we have to return the maximum, right? So I'll say simply return me the maximum of match and not match, right? Now, what can be the possible? Okay, so now let's discuss the base case. What will be the base case? I'll say that if at any point of time I've exhausted any of my indexes, that means I have traversed one string completely, right? Then in that case, I need to simply return a 0. I think we're good to go. Let's quickly run it. And we're getting the right answer. I'll not submit it because we'll get a TL, right? Now let's quickly discuss its time and space complexity. Okay, so this is the code that we just worked upon, right? So let's talk about its time and space complexity, right? And then I'll have a quick dry run for the same. So basically what is happening here is, you see there are two times a recursion call is being made, right? So basically one is for the condition of match and the other is for not match. So we'll have an exponential time complexity. And when you talk about the space complexity, that is O of n, which is because of recursion stack space. Now, why do we have it and why is the time complexity exponential in nature? You'll know the answer just now when I'll dry run it. So let's quickly have a dry run. Okay, so I'll be drawing both the recursion stack space and the recursion tree so that you understand it. So let's take the example that we had the text one as A, B, C, D, E and the text two as A, C, E, right? This is text one string. This is text two string. Now what happens is, or I'll write it somewhere which is neater. Okay, so the text one string that we have is A, B, C, D, E, and the text two string that we have is A, C, E, right? So what happens is the first call is made for solve. As you can see that the value of n in this case is 5, right? And the value of m is 3. So now what happens is I'll call the solve function here. It gets added into my recursion stack space and n minus 1 says 4, m minus 1 says 2. So initially my pointer is pointing here for text 1 and text 2. And I have this first call that is being made. I'll go to the solve function. I'll check that is either one of them less than 0. No. So I'll go for match. So what happens here is, we'll say that initially the value of match is minus 1e9. Now I'll check that is the character at text 1i is equal to text 2j. And we see yes, both of them have an e. So what you do is you change the value of match. You make it 1 plus call a solve function, right? So it is calling a solve function wherein what I am doing is I am decrementing both of them. right? So when I decrement both of them, I had 4, 2, I'll have 3, 1. So now this gets added into my recursion stack space and my pointer is pointing towards it. So I again come back to the solve function. I'll check that is 3, 1, either one of them less than 0, and the answer turns out to be no, it is not less than 0, right? So what I'll say is, I'll say, okay, now we'll have a match condition for this. So match is initially minus 1e9, and we'll check that is whatever present. Now my pointers are here, right? So I'll check that whatever is present on text1 index 3 and text2 index 1, are they equal? I'll say no, they're not equal. So my match remains minus 1e9. I will not go in this if block. I'll come to not match, right? So for not match, I'll say take the maximum. Now when I'm taking the maximum, I'm calling the first solve function. Therein what I'm saying is decrement the value of I. When you decrement the value of I, you get a 2 and j remains as it is, right? So when this call is made, this is added into the recursion stack space, and now my pointer is pointing to s2, 1. So that means now I am standing somewhere here. That means my pointer on this string 1 increased, but string 2 it remained the same. Now what happens here is, now I'll again check that are they less than 0? No, 2 and 1 are not less than 0. So for this, I'll have a match condition, which is initially minus 1e9. And then I'll check that are these equal? And I see yes. Both of the indexes, text1, 2 and text2, 1 have a C. So that means they have the similar. So this M becomes 1 plus it further calls for the solve function, right? So it says 1 plus, you call the solve function and you decrement both of them. So you get 1, 0. Now S1, 0 is present in my stack and my pointer is pointing towards it. So what happens here is, when it is now called, I'll check that is any one of it exhausted. So when you say that, I said no, it is not yet exhausted because I'm still on the 0th index, right? So it is still greater than equal to 0. I want something that is just less than 0, right? In a minus index. So no, the base case is still not satisfied. I'll have a M for this. So M is initially minus 1e9. I'll check that whatever is present on text 1, 1, that means B, and text 2, 0, A. Are they equal? No. So the match remains as it is. And then we'll go to not match. When you go to not match, you will again take a maximum, right? So I'll zoom out a little. Yeah. So you will again take a maximum. Now what you will say is, you will say that whatever is present on the ith index, you decrement it and let the j be as it is. So now my I is also 0 and my j is also 0. This gets added into my recursion stack space and my pointer is pointing towards this. My base case is still not satisfied, right? So I'll have a match for it. Match is minus 1e9. Now it will check that is A, that means text 1, index 0. Is it equal to text 2 index 0? It will say yes, it is. So what happens is, I'll increment M and it will become 1 plus S, and we'll decrement both of them. We'll have minus 1, right? And this S minus 1 is added into the recursion stack space, and now my pointer is pointing towards it. As soon as this function call is executed, what happens is, I see that yes, both I and j are less than 0, and even if at least one of them is, it is applicable. I have to return a 0. So here I'll get a 0. So 1 plus 0 makes it 1. This function gets popped out because it has completed. Now it says that for this function that was s0, 0, my match function is giving me something as a 1. So I'm getting a 1 here, right? So what happens is, s0, 0 function is now on the top of the stack here, right? So what does it say? It says that, okay, you figured out the match statement. Now figure out if it is not matching, right? So what happens is, now for this function call, and we were working with match, right? So we'll work out the not match condition, right? And then the execution continues. So from this, what we understand is, see, the recursion tree and the stack space will be very, very big. And it will take a lot of time for me to completely build all of it, right? So But from this dry run, what you understand is that at any point of time, you have two choices. The first choice is that whatever is present for the string 1 and string 2 for the index I and j, they are either matching or they are not matching. And for even not matching, you have two conditions, right? That is, you are either moving I, keeping j as it is, or vice versa, right? So that is why the time complexity turns out to be exponential in nature. And as you see in the worst case scenario, this was the recursion stack space, right? So in this worst case scenario, this will have almost all the possibilities. So it becomes O of n, right? So we have talked about the recursion code, right? Whenever we talk about optimizing recursion, we know that we can optimize recursion using something as DP. Now, what is DP? DP is dynamic programming. So basically, what does dynamic programming say? It says that whatever you have computed, you store it somewhere, right? Because if you would have completely built all of this tree, we would have seen that we were having something like overlapping subproblems, right? So whenever you have overlapping subproblems in recursion, you can optimize it using DP. It says that you store whatever you have computed at one place and you use it directly rather than recomputing it, right? So basically, I'll quickly copy paste the code down here. Okay, so this was the code. Now we'll just do subtle changes to convert it into memoization. What is memoization? Memoization is a top-down approach, right? In which we use a DT vector for storing the pre-computed values so as to recompute things over and over. Now, what happens is basically whenever we talk about DP, right, we have to understand that whenever you have something like this, that means I is less than 0, j is less than 0, then you have to return a 0. In that case, you will not have these indexes, right? So, what you have to do is you need to increment the index, or you can say the increment the size of the DP vector. And you can assume that if I am saying I is equal to 0, in the parallel universe I'm considering it as I plus 1 being 1, right? So here we'll have certain changes. What are these? I'll create a 2D vector DP. Why am I creating a 2D vector? Why not a 1D vector, 3D vector? See, basically a DP vector being of which dimension depends upon number of parameters that are changing in the recursion function. So if you see in the solve function, both the values of I and j are changing, right? So similarly, what happens is here I'll create a 2D DP vector and I'll pass my DP here. I'll simply put a check here that for that particular index, if that is not already computed, right? For example, if it is already computed, that means do not recompute it, do not go into match, not match, and again have exponential time complexity. You simply return whatever you have stored. And here, as we were figuring out the maximum, we'll store it for every DP of I comma j, right? I hope I am clear. Basically, this memoization code, it boils down the time complexity to O of m into n and a space complexity of O of m into n plus O of n, that is the recursion stack space. What is m and n? M is the length of string 1 and n is the length of string 2. Now let's quickly make these changes in our code and see if the code is working fine now, or do we need to further optimize it, and if we do, how? So this was the code that we had written for the recursion case. Now what I'll do is I'll quickly create a DP vector here, right? As I talked about the index increment, because we have a base case where we are considering an index which goes into negative, and we know that in practicality there won't be any such index, right? So I'll create a DP vector of m plus 1 vector int n plus 1, right? Now, rather than passing n minus 1, m minus 1, as I've moved every index by 1, I'll simply pass n and m. And what I'll do is, I'll have this case as if I is equal to 0 or j equal to 0. And I'll add a dp condition here. First of all, I'll add dp vector here, the 2D vector we've just created. So it will be vector int ampersand dp. And here I'll say that if dp of I j is not equal to minus 1, then in that case, you return me dp of I j, and in my recursion calls, I'll add the dp as the parameter, right? So here, and we'll add one here. Now, when I'm finally computing the maximum, I'll be storing it so that I do not have to recompute it over and over. And we're getting the right answer. Let's see if it gets accepted. Or do we get a TLE? Okay, we're still getting a TLE. So basically, for this code that we have just written, we're still getting a TLE. So let's see how we can optimize it. Okay, so this is the memoization code that we have just written. Herein, we know that the time complexity was O of m into n and a space complexity of O of m into n plus O of n for the recursion stack space. So still it is not being accepted. That means there needs to be certain changes. So what changes possibly we can have is I can eliminate this O of n, which is because of my recursion stack space. To do this, what I'll use something as tabulation. So basically, whenever we talk about memoization, it is a top-down approach. But whenever we use tabulation, it is a bottom-up approach, and it is iterative in nature. As memoization is recursive, it is a iterative approach. So as it is iterative, we do not have to maintain something like a recursion stack space. So this gets eliminated, and we just have a time complexity of O of m into n and space complexity of O of m into n, right? So for converting the given code into a tabularized version, what I'll do is basically whatever here is my base case will be utilized to build my tabulation approach, right? So I'll have a DP vector, right? That is a 2D DP vector, and its size will be n plus 1 and m plus 1. These are the sizes corresponding to it. This is not the way you write it. I'm just writing it for the fact of pseudocode for you to understand how I'll be making the code from memoization to tabulization, right? So what I'll do is I have this DP vector and I'll initialize everything to 0, right? So after that, what I'll do is I'll say, see, the base case is also handling 0 index and it is again returning 0. So I do not have to do specifically anything for it because initially my 2D vector is initialized with 0. Next, what I'll do is I'll run a for loop for I is equals to 1 till I is less than equal to m, and I'll run another for loop for j is equals to 1 for j is less than equal to n, right? I'll run these two loops. Now I'll not do anything new. I'll just pick up this part and put it right here in the terms of dp vector, right? So what I'll say is, I'll say that if the text I minus 1 is equal to text j minus 1, right? In that case, for dp of I comma j, what you do is you will say add 1 to whatever was present in dp I minus 1 and j minus 1. See here I minus 1, j minus 1, we are adding a 1, right? Or what you will do is you'll simply have an else case wherein you will say that dp of I comma j is the maximum, and you'll take out the indexes that we have, that is dp I minus 1 where j remains as it is and dp I j minus 1. It is as simple. So when, and then finally you can return something as dp of mn, right? This is the final return that you will give. So if you look at this, this makes a time complexity O of m into n, which remains the same, but it decreases that extra recursion stack space you were carrying alongside. Let's quickly make these changes into our code and see if it's working fine or can we further optimize it. So basically, this was the code that we had written and it was still giving a TLE after memoization also. What I'll do is, I'll simply comment these lines out, and now initially my PP vector is initialized to 0. Now I'll run a for loop for int I is equals to 1, I is less than equal to m, I plus plus. A second loop for int, okay, the first one goes till n. So I need to change here, right? For int j is equals to 1, j is less than equal to n, m, j plus plus. And now what I'll say is, I'll say that if, I'll simply copy paste these conditions there, right? So I'll say that if x1 I minus 1 is equal to x2 j minus 1, right? That means that both the characters in both those different strings are same. So in that case, for dp of I j, you will add 1 to dp of I minus 1 and j minus 1. Else, you will say the dp of I j should have the maximum of dp of I minus 1 j, comma dp of I j minus 1, right? And then we'll finally return dp of n comma m. Let's quickly run it and see if it's working fine. It is. Let's submit it. So yeah, it is submitted. Now let's have a dry run for it and let's discuss time and space complexity. So basically what is happening here is I'm going to have a dry run, right? Now when I talk about the dry run, I know that my first string is A, B, C, D, E and my second string is A, C, E, right? So 0, 1, 2, 3, 4 and I have 0, 1, 2. What happens here is I'm creating a 2D DP matrix. So as you can see that my n value was 4, 4 plus 1 makes it 5, 3 plus 1 makes it 4. So I'll have 5 cross 4 matrix. So that means 5 rows and 4 columns. 1, 2, 3, 4. And let's create one more. I have 0, 1, 2, 3, 4. And I have 0, 1, 2, 3. Right? Initially, everything is initialized to 0. This is my DP vector. Right? Okay. Now this loop begins. I am at I is equals to 1. J is also equal to 1. I'll check that if the value at text I minus 1, j minus 1, that means text 0 index, text 1 0 index, text 2 0 index, are they same? So you see that, yes, they are same. In that case, add 1 to dp I minus 1, j minus 1. So I minus 1, j minus 1, if you look at it, because the I value was 1 and j value was 1, so 0, 0. So you look at this block, it is already 0 and you add a 1 on dp I comma j. So for 1 comma 1, you will have a 1. Then after that, as you've completed the if condition, you will not go to the else condition. Now I remains 1, j becomes 2. So now you will compare for I minus 1. So I minus 1 is 0. So that means for text 1, you are still standing on the 0th index. For text 2, you are on the first index because 2 minus 1 makes it 1. So you are standing on C. So you'll see, is A and C common? Is A or C equal? You'll say no. So you'll fall into the else statement. So dp of I comma j, that means dp of 1 comma 2 will have maximum of dp I minus 1 j. I minus 1 is 0 comma 2. So if we see 0 comma 2 has a 0 and 1 comma 1 has a 1, right? So in that case, you will say that my dp 1 comma 2 will have its maximum. So in either case, I am filling whatever is either on its top or its left hand side, right? Similarly, now my j becomes 3 because it can go till m. So m, as you know, is 3, right? So I am standing here and my I value is already 1. So I'll compare for the 0th index and the 2nd index, and I'll see that A and E are not equal. You fall into the else condition. You will check for its upper one, that's 0, or its left one, that is 1. So it will increment to 1, right? So after that, you've exhausted this. I becomes 2, and now J will iterate from 1, 2, and 3. So when I is 2, you're standing for you're comparing these strings, right? Why did we increment the string was because the base condition that we had was a negative and we could not cater that. That is why. But when you are working on actual strings, you have to work with the actual indexes. That is why we are subtracting 1 from it. So 2 and 1 you have, right? So if you see, what you have is text I minus 1. I is 2, 2 minus 1 is 1. So that means you're standing here. You have a B and you have to compare it with 1 minus 1, that is a 0, A. They are not equal, you'll fall into the else condition. So you will say BP 2, 1. That means second row, first column. That means this one. Here you have to take the maximum of dp I minus 1j. So if you minus 1, that is 1, 1. So here on 1, 1, as you see, you have a 1. So you have to figure out between, you have to take a maximum between 1 and dp I j minus 1. So dp I was 2 and j minus 1 makes it 0. So 2, 0 is 0. So that makes it 1, right? So again, for this portion, you have to compare these two, the upper and the left. Then you go to the next index, you will again see that now you tell me for index 1 and 1 for both of them, right? Are these equal? So you have a B and you have a C, so they are not equal. So you'll take a maximum and you'll again have a 1. So basically this matrix is storing the number of, or you can say the longest common subsequence length. Okay. So now when you go to 2, 3, you will be comparing the 1 and the second. So 1 is B and the second index for text2 string is E. So B and E are not equal, right? So in that case, you will again fall into this else statement. You will take the maximum and you will again get a 1. Now you will be moving forward with I is equals to 3. J will be ranging from 1, 2, and 3. Right? So when you are now, you have to compare C with all of these, right? So first you compare it with A, you do not get anything, you'll take the maximum. But as soon as you compare it with the second index, right? So that means whenever you are on 3, 2, here you will see that they have this similarity. So you have to take 1 plus whatever was I minus 1, j minus 1, that is 2, 1, that makes it 2. Now, when you come here, on 3, 3, that means you are comparing the second index of text1 and the second index of text2. So that is C and E, they are not equal. You take the maximum, you will again get a 2. As you complete it, you will finally get a 3 here and you will return it. So this is the approach. The time complexity is O of n into m and the space complexity is O of n into m. Thank you so much for watching the video till the end. Please like, share and subscribe. If there's anything you want to discuss, feel free to comment. Thank you.